In this video, I'm going to show you how to use this rationalizing the denominator to do something a little strange. We're going to prove that the square root of 2 is irrational. All that means is if you try to write square root of 2 as a fraction, so a and b are natural numbers, which means they're just like 1, 2, 3, 4, just your regular old fractions. You can't do that. So there's no way to get square root of 2. All right. This was first proven by a guy named Euclid in like 2000 BC. He used the fact that you can write any fraction in lowest terms, which in turn that uses something called the prime factorization of the natural numbers. Which prime factorization, it's not that hard to get, but it's definitely prime factorization says that if I have any natural number, I can write it as a product of prime numbers. You did this in elementary school. You took 24 and said, oh, that's 2 times 3, or sorry, 8 times 3, and then 8 is like 2 times 2 times 2. So, yeah, you can break down anything until you get primes. That's not the easiest thing in the world to prove about the natural numbers. So in this video, I want to give you a way to get this that doesn't use this big, huge tool here called prime factorization. It only uses the well-ordered principle of the natural numbers. Which what that says is that if I have any set of natural numbers, there's always a smallest one. Right? I mean, intuitively, you can imagine if I give you a bunch of numbers out of 1, 2, 3, 4, I mean, I could keep giving you bigger and bigger numbers. There might not be a biggest number in this. I could give you a list that goes on forever. But even if the list goes on forever, there's still always going to be a smallest number in that list. So that's all we're going to use about the natural numbers in this proof. All right. Okay. Well, instead of doing square root of 2, let me actually do square root of 2 minus 1. It's a little more convenient. Basically, it's going to let us do our rationalizing the denominator stuff. So let's say that we've somehow managed to write this as a fraction, and we're going to write it where b is as small as possible. And you might be saying, hey, it looks like you're putting a fraction in lowest terms, just like Euclid did. Well, I am, but not really. I mean, Euclid, you need to know that to put a fraction in lowest terms, you can kind of cancel factors from the top and the bottom. And I mean, like if both of them are even, you can divide them both by 2. You need to know kind of what that process of putting in lowest terms is. For this proof, really all we're using is this well ordering. I don't have to know anything about factoring. I don't have to know about dividing or putting a fraction in lowest terms. If I can write this as a fraction, because of this well ordering of n, there has to be a fraction that has the smallest possible denominator. So I'm just saying, okay, well, since n is well ordered, I want to write this as a fraction, and I want the denominator as small as possible. All right. Well, the first thing I want you to see is that a is less than b. That's one of the reasons I wanted to do this minus 1 here. Square root of 2 is like 1.4 something. I subtract 1, so I've got like 0.4. So whatever a and b are, a has got to be smaller than b. All right. The next thing, let me do b over a, which would be 1 over square root of 2 minus 1. And let's rationalize the denominator. So if I multiply this by root 2 plus 1 over root 2 plus 1, this is root 2 plus 1 over, on bottom, root 2 squared is 2, minus 1 squared is minus 1. 2 minus 1 is 1, so this is just root 2 plus 1. That's very similar to what I started out with. I started out with root 2 minus 1. If I subtract 2 from this, if I just go ahead and subtract 2 from both sides here, I'll have root 2 minus 1 is b over a minus 2, which is b minus 2a over a. Now, I'm going to tell you that we're actually done. Why is that? Well, a is less than b, right? I said at the beginning I wanted to write root 2 minus 1 as a fraction with the bottom as small as possible. But here, I just wrote root 2 minus 1 as a fraction, but I made the denominator even smaller than the smallest possible one. So the set of possible denominators, you can always get smaller. And since we know n is well ordered, well, you can't always get smaller. You have to hit the smallest one eventually. So the only way this could possibly happen is if there's actually not any denominators. So there's no way you can possibly write root 2 minus 1 as being a fraction. That's it.